So previously we have discussed the equivalent circuits of the transformer, including the approximate equivalent circuits. Herewith we are going to discuss the voltage regulation, which is one of the important performance measure for the transformer operation. The output voltage of the transformer shall vary only within the narrow range when the load varies. So this particular is the requirement. The load variation can be in terms of the magnitude, or it may be because of the power factor. The constant voltage is the requirement because of the sensitive nature of the loads. This sensitive nature of the loads may come because of the industrial, commercial or domestic usage. However, the voltage cannot be maintained at the constant level because of the winding resistance and the leakage reactance. So these particular, the resistance and the leakage reactance are basically part of the practical transformer. So the effort is there to minimize them, but they cannot be eliminated. So how the voltage regulation is defined? The voltage regulation is defined as the change in magnitude of the secondary terminal voltage expressed as percentage of the rated secondary voltage when the rated full load of a specified power factor supplied at a rated voltage is thrown off. But that thrown off is having a sense, it is reduced to no load with primary voltage kept unchanged, or you can say constant. So in mathematical term, this particular is expressed as V20 minus V2FL upon V2FL, where say V2FL carrying the sense of rated secondary voltage at full load of a specified power factor, where say the V20 it is the secondary voltage when the load is thrown off. So these particular terms V2FL and V20 will be clear when say we are discussing the equivalent circuit. So previously we have developed the equivalent circuit referred to the primary and the secondary. So when say we are referring to the secondary, the approximate equivalent is represented likewise, where say the net resistance is coming out to be Re2, reactance is Xe2. The magnetizing branch can always be neglected. The input voltage is coming out to be V1 dash. So this particular you can say obtained after having say scaling the parameter with the turns ratio as explained previously. While say the referring to the transformer equivalent with respect to the primary, so the secondary side parameters are referred to the primary side, and the net resistance is represented as Re1, net reactance is to be represented as Xe1. So in this particular, when say we are saying the rated full load means what is say the terminal voltage, in this particular it is V2, here say it is V2 dash. When say we are having the load is thrown off, so that particular is the V20. When say the load is thrown off, when say the input voltage is kept unchanged, so that will be the V1 dash in this, whereas in this it will be V1. So the phasor equation, which is the KVL relationship, is dictated by the expression like this for the equivalent referred to the secondary, and this particular will be the KVL relationship when say it is referred to the primary side. Now, as we have made clear in the previous lecture that the performance is unaffected when say that we are referring the transformer either on the primary side or on the secondary side. Only difference which is arising, it is the numerical value. So keeping that particular thing in mind, we will be having a simplified arrangement. So the subscript 1 or 2 have been dropped, except this particular V1 is having a sense of input, this particular V2 is having a sense of the voltage at the load terminal. So with this we will be having a development of the phasor diagram likewise. So the phasor diagram is This particular phasor diagram is for the lagging power factor load. It has been explained many times. So V2 is a reference, the current is lagging. Correspondingly, you have marked the IRE and IXE, or you can say the phasor voltage drop associated with the resistance and the reactance, and correspondingly the net input voltage is marked. Now we have to calculate this particular V1 likewise. So we will be making use of the symmetry of the arrangement. This particular is the power factor angle theta. So when say this particular angle is theta, this particular angle will also be theta, this angle will also be theta likewise. Now as made very clear that there is an effort to reduce the winding resistance and the reactance. So you can say the voltage drop in the winding impedance is small in comparison to the terminal voltage. So because of this, whatever say the voltage V1, which is equivalent to OA length, is approximated as OC. So V1 is approximated as OC. So this is an approximation where we will be able to find out the mathematical relation. However, the exact calculation can be worked out if suppose the numerical values are coming out to be there. However, it is not losing any significant accuracy. So OC in this particular, it will be equal to the OB plus BC. BC is exactly equal to the DE, so that will be equal to OB plus DE, and that particular is defined as OB plus DF plus FE likewise. So correspondingly this DF component will be equal to the IRE cosine of theta, whereas this particular component EF will be equal to the IXE sine of theta. So this particular is the arrangement for the OC. The difference between the input and the output voltage will be IRE cosine of theta plus IXE sine theta. This particular plus sign is coming out because the load is of lagging power factor nature. When say we are going for the capacitive load or the leading power factor load, the current is leading to the secondary voltage V2 likewise. So this terminal voltage is marked as it is. IRE and IXE, you can see the voltage drop in the transformer windings are added likewise, and the V1 is marked. So you can easily make a comparison. This particular V1 length is coming out to be lower in comparison to the V1 length which has been obtained for the lagging power factor load. Similarly, going by the same analogy, we will be calculating the OC, an approximation to find OA likewise. So this particular is giving us the value V2 plus IRE cosine theta minus IXE sine of theta. This difference is approximated like this. So IRE cosine theta minus IXE sine theta. So here say in the leading power factor, this particular is arising the negative sign. As a summary, this is the arrangement for the RL load. So it is having the positive sign. Here say RC load is having the negative sign. When say these two relations are combined and represented here, so they are represented with the plus minus sign, where say plus stands for the RL load or the lagging power factor load, where say the minus sign stands for the RC or the leading power factor load. The voltage regulation is always positive. This particular information is true for the resistive load as well, where say the power factor will be unity. So sine of theta will be 0, cosine theta will be 1, so the voltage regulation will be positive. For the RC load, the exact nature will be decided by the power factors, which is the cosine theta sine theta value. Now the reactance is coming out to be predominant in the transformer case. So that particular is also deciding the factor. So correspondingly the zero voltage regulation is achieved for the RC or the leading power factor load when say we are making this particular equal to the 0. So correspondingly tan of theta is coming out to be RE upon XE, and power factor, or you can say the cosine of theta, is obtained correspondingly by the right angle triangle property, or you can say the impedance angle pertaining to the transformer winding. Similarly, this negative sign also signifies that the negative voltage regulation can also be achieved, and this particular is resulting when say the sine of theta value is coming out to be greater than or more than theta z. So these two you can say easily calculate with the expression of the voltage regulation for RC load. Now as mentioned that for RL load the voltage regulation is always positive. So the maximum voltage regulation is resulted pertaining to the RL load situation, and this particular is happening because only the power factor, or you can say the theta angle, is varying. So you can calculate this particular condition derivative of delta V with respect to the theta and making that equal to 0. So this is suggesting the condition of maximum voltage regulation. So this particular is achieved, obtained, and correspondingly if you are writing the power factor, so this is coming out to be like this. And as an example, we have considered the 100 kVA transformer having a primary and secondary parameter likewise. So the number of turns are 400 and the 100 respectively. Correspondingly, the resistance reactance values are also specified. The supply voltage is 2400 volt, and we are interested in calculating the equivalent resistance and reactance refer to the primary side, the voltage regulation at 0.8, lagging power factor, voltage regulation at 0.8, leading power factor, and then find power factor for zero voltage regulation. So as say the turns ratio is 4, that particular is mentioned. So 400 upon 100 is equal to 4. The equivalent resistance refer to the primary. So that particular will be R1 plus A square R2. It is evaluated as 0.54 ohms. Reactance refer to primary is evaluated as 1.98 ohm, and the primary rated current, so it is of 100 kVA, so 100 multiplied by the 1000 divided by the voltage level, so this is giving rise to the 41.67 ampere current. We are interested in calculating the voltage regulation at lagging and leading power factor. So at the lagging power factor, the expression is IRE cosine of theta plus IXE sine of theta. So here say the plus sign is important. Correspondingly we calculated likewise. So 67.5. Now this is coming out to be positive. So that suggests that the reflected secondary voltage will be less, or you can say the voltage regulation is positive. So that particular value is 2.81. Now the secondary voltage is calculated with the help of reflected secondary voltage. So this particular 2400, which is the input, minus 67.5, it is giving the reflected secondary voltage divided by the turns ratio. So it is resulting into the secondary voltage, and that particular is coming out to be 583 volt. On the similar line, we have calculated the voltage regulation for 0.8 leading power factor. So for the leading power factor, this negative sign has to be there, and that is resulting into the value like this. So this particular is suggesting that the secondary voltage or load voltage is coming out to be more than the input voltage. However, the voltage regulation is marked negative, and the secondary voltage is calculated after calculating the reflected secondary voltage and dividing it by the turns ratio. So that is 607.9 volt. Correspondingly, we can calculate the condition for the zero voltage regulation. So that the direct formula, and we have substituted as here we have to specify the leading nature, so that is indicative of the RC load. Out of this, if suppose we are giving the numerical value under consideration, the resistance value is 0.54 ohm, reactance value is coming out to be 1.98 ohm. So the reactance value is typically about 4 times the resistance value, and that suggests that the reactance is coming out to be predominating in the voltage regulation. So as a summary, the leakage reactance is dominant in deciding the voltage regulation. This voltage regulation term is always positive for the unity power factor resistive load and the lagging power factor loads. The voltage regulation may have zero or negative value for the leading power factor load depending on the power factor. So corresponding to the zero voltage regulation, we can obtain the relation where say the maximum voltage regulation is achieved at the lagging power factor load, and the relationship is coming out to be like this. In the next, we will be discussing other performance measures like the losses in the transformer and the efficiency. For further reading, you can refer these two textbooks. Thanks.